Chennai. I especially want to welcome our guest, Dr. A. Srinivasan, Head of the Department of Biotechnology, National Institute of Technology, Andhra Pradesh. Our HODs, Dr. R. Bhaskaran sir and Dr. N. Venkatesh sir, my colleagues and participants from various institutions. To start with, chemical reaction engineering is a specialty in chemical engineering or industrial chemistry dealing with chemical reactors. Chemical reaction engineering aims at studying and optimizing the chemical reaction in order to define the best reactor design. Hence, the interaction of flow phenomena, mass transfer, heat transfer, and reaction kinetics are of prime importance in order to relate reactor performance to feed composition and operating conditions. The main objective of chemical reaction engineering research is the design and operation of industrial reactor to conduct chemical reaction more effectively at an industrial scale. Such effort requires knowledge from multiple disciplines, and reaction kinetics is one of the most fundamental knowledge needed. Our guest will explain about the fundamentals and importance of reaction engineering in chemical engineering discipline and other discipline. Now, I will hand over this session to our guest, Dr. A. Srinivasan.
Hey, thank you very much for your introduction. Uh, I just start. Uh, I mean, required few minutes because the operating system what I'm using is different now. We know.
Yes, sir. Tell me, sir.
Uh, whether slides are moving.
No, sir. No, sir. Actually, I can able to see your desktop only, sir. Kindly open your slide, sir.
Open.
Hello, sir.
Yes. Few
Yes, sir.
minutes.
Kindly share your screen, sir. Okay, sir. Okay, sir.
Uh, Can you able to see this one?
Yeah, sir. Yeah, sir. Now it's okay, sir. Kindly start your presentation, sir.
I think I'm not able to move. Whether it is moving?
No, sir, it's not moving, sir. We can able to see only your first slide, that is fundamentals of biological reaction engineering.
Once again, I will share my entire window. So
Okay.
that will help, I think. Now it is fine.
Now it's okay, sir. Now it's okay, sir. Yes,
Okay.
sir.
Okay. Hey, uh, I thank for this opportunity to Vinod and Karthik and other colleagues. It's my mistake. It has been long time because my system suddenly got some crashed, so I could not able to connect within the time. So I don't extend further. I'll just continue with the presentation. So today I'm going to talk about the fundamentals of biological reaction engineering. Though I term this one as biological reaction engineering, it's nothing but a chemical reaction engineering only. And we try to borrow many concepts from here to biological system. That's why we keep this chemical engineering as our background, and thereby I am presenting the biological reaction engineering fundamentals. So just a little bit remarks about my institute. Our institute started in 2015 and it is located in Tadepalligudam at the historical place Second World War runway. We constructed at Second World War runway besides that one. And it is located near the National Highway 60, Chennai to Kolkata Road. And it has our institute has 8 departments and offering BTech program and MS by part time for all of 8 branches. And we are also offering PhD full time and part time for industry people and academician. So it is those who have good connectivity with nature loving or something like that, this is the best place to live in. We have, very close. We have a Godavari river, and where we can have many dams were built there. It's a good place to see. Apart from that, we are living in a place where the export of freshwater aquarium based products are heavy, and it is 20 trillion dollar business they are carrying out at Bhimavaram, which is also very near to us. So I have shown the route map from Vijayawada to our institute, which is 100 kilometers. So we are the youngest entity. We started in as a 31st one. Now my talk will have my talk will be covering this kind of topic one, definition and fundamentals of reaction, and homogeneous reaction. I'm talking about the purpose of finding kinetic expression or rate equation, and ideal reactor design aspects and method of finding kinetic expression, heterogeneous reactions, a small introduction, and few examples of reactor design, and finally acknowledgement for that. So whenever, since I'm talking to the chemical engineering people, and all people have a different opinion for the chemical engineering definition for chemical engineering. Few people say that any raw material you give it to us, we'll try to process that one, and we'll give you a better product which will serve the society need. That's what they define. So the feed can be gaseous, liquid, or solid, or waste, anything. And the reactor is our core part where we will be doing our reaction. And the reaction, the reactor can be a different type. I'll talking about that one in the rest of the part. And finally, we'll be getting a product. So it looks like very simple, but it has its own complications. That I also explain when I go to the further slides. And this was a chemical engineering definition. So if you see the biotechnology definition also, which resembles the same, we'll also handle all gas, liquid, solids, everything as a feedstock, and we'll also use your bioreactor, chemical engineering, what people used to do, but we built for our own purposes. So we use a cell or enzyme to perform the particular reaction. We use these two systems only. So these two systems, though it is two systems, among cell you have a different variety of cells. Bacteria itself, we have n number of bacteria. Fungi itself, we have n number of fungal groups. All I mean, yeah. Enzyme itself, we will have variety of enzymes. So there, our role are going to be much more important. Apart from the construction, those are all very important things. And then we'll end up with some product which we say that it is eco-friendly, greenery, and it does not require high pressure and high temperature. Safety wise, we are compromised. So those points we will propose as a bioprocess engineering as advantage towards the chemical engineering process. Huh. Now, the wonder is in chemical reaction engineering, let's say you do reaction and you get as one product and unreacted substrates. But it is not the case with the biological reaction. You can see one carbon is entering and the carbon will be utilized for the same survival of the organism as well as it generates a number of products. So how to enhance our desired product irrespective of the product it produces. So that is the actual trick in the entire bioprocess engineering. We do some changes in the external environment and then we try to see like what best we can get in the output. So that's how the conventional bioprocess engineering works with these cell culture systems. Okay? So I'm not talking about much because if I go into detail, then I'm talking about metabolic engineering. Now, so for any chemical reactor system or biological system, we'll be talking about basically we'll talk about the reaction as homogeneous and heterogeneous. If you see the first figure, you cannot find any phase differences, the block box. And another one, you can see some kind of invisible or different phases are there. And for an example, I have given one like if you add a milk, water into the milk, you don't require a physical stirring. On the adding itself, it gets mixed because those are all visible each other. So such a systems we call that one as a homogeneous system because you don't have any phase difference or you don't have any kind of layer separation. Nothing will happen. But if you see the second one, I am just trying to add a sugar into the water. But if you leave it like that, the sugar will be there as a solid and your water will be there. So these are all two different phases. Whenever you have a two different phases, your additional effect will come, that is the mass transfer. We will be trying to use your spoon or whatever maybe to stir that one so that we can we can create some kind of concentration gradient or we can make the solution uniform so that the distribution or dissolution will be better. So these are all the problem comes when we talking about heterogeneous systems. So yeah, homogeneous and heterogeneous systems, the difference mainly we have a same phase or we have miscible liquid which react each other. Then there is no problem with the mass transfer. But whenever we try to go for a heterogeneous system, we have a phase difference or we have a immiscibility or which do not mix each other. So then there will be a layer separation. So the mass transfer comes into the play. I'll be talking about this difference minutely when I'm talking about heterogeneous system. So there are in Levenspiel, if you see homogeneous catalytic and non-catalytic system, he denoted that see the fast reaction such as burning of a flame, which can be considered as homogeneous or heterogeneous system. And most of the reaction what we are carrying out colloidal system, enzyme or microbial system, which can lie in between the homogeneous and heterogeneous system. So I can consider homogeneous also. I can also consider a heterogeneous system. It depends upon situations. So I'll explain like what kind of situations, so what assumptions we will make it. These are all assumptions we will be trying to make when we try to create some kind of design for the reactors. And in definition also, the people define the rate as the number of moles changes in the reaction, either it is consumed or formed, divided by the unit volume of the reaction, unit volume of the reaction. So that works for only for the homogeneous system. What happened to the heterogeneous system? If you see the heterogeneous system, it does not work. And typically you can see here the heterogeneous system, the weight of the solid you can express as 1 by W. Instead of this volume, I can also use the weight of the solid. In the case of solid and liquid reaction, I can also use it. Sometimes if it is immiscible liquid, and the interface area also matter, because through which it can exchange the reactant, right? So the surface area also sometimes we will be using in order to define the rate. Like that, the solid volume also I can use it. Similarly, I can use it the unit volume of the fluid also in the case of heterogeneous system. So from here to here, if this is simplest system, there is no phase differences, nothing will happen. But in the case of heterogeneous system, you have a phase difference. So mass transfer plate comes to the picture, and in the rate definition also, you can define your rate with a different notation. Either use your solid as your base, or the weight of the solid you can keep it as a base, or surface area of the interfacial area of the system also you can use as your you can use it as in the rate expression. Now, so before going into the kinetic part, why we need to deal with the kinetic part? That is very important, because when I have learned like this, like I need to propose some kind of rate expression. So I'll be trying to fit with my rate expression. At the end of the fitting the data, what I am going to do with this kinetic expression, that matters, right? So this one I got it clarity from my professor only. I try to explain like what is the need for finding a kinetic expression. So again, if you see the Levin scale, he said the output of performance equation of any reactor, the output is the function of input, the kinetic pattern and conducting pattern. So the input is like what you are giving in, or what you supposed to supply, and the kinetic pattern talks about the chemical parameter and physical parameter. So in kinetic, the chemical parameter means you can the reactant, how fast it is getting reacted, and the physical parameter is like if you have a heterogeneous system, those effect also we need to incorporate in the kinetic term. Whereas in the conducting pattern, either you can use batch, you can use continuous system. In the continuous system, we have only two reactor. One is plug flow reactor and mixed flow reactor. So, depends upon the contacting between the reactant, how you want. So, based on that one, you can choose your batch system, continuous system. So, for an example, if you have a feedback inhibition with your substrate, so you cannot use your batch system. Instead, you can go for a continuous system where your reactant can be added, a little quantity over period of time. So by which you can reduce the feedback inhibition as well as you can carry out the reaction. So these kind of conducting pattern also influence your output pattern. So any output, it is depends upon these three functions only. And this one I will try to show you in the design equation also. Now, I have shown very simply the design expression everywhere, and you can see in every design equation for the batch system, plug flow system, or mixed flow system, in the design equation you can see some kind of minus RA. What is this one? This is your rate expression. So this is what I am trying to find at my laboratory, the order or the kinetic constant, all those things I am trying to find. This one only, the rate expression. This is the ultimate aim of finding a kinetic expression. Once you find your kinetic expression, try to substitute over here, and then you will be evaluating the volume which you want to build it, or the conversion which you try to achieve from the particular reactor. Okay, this is what the ultimate aim of finding a kinetic expression. The kinetic expression just helps in the conceptual design of the reactor. Now, before going into the kinetic expression, I'll try to give you an overview of the ideal reactor which we see. First one is batch system, another one is the plug flow system, third one is the mixed flow system. Okay, and the definition also I'll try to give. So, as a chemical engineering, what we do, we try to write a material balance for any system where it can be any reactant can be consumed, or it can be a reacting system or non-reacting system. If it is a reacting system, then the rate of consumption, all those terms will be coming in. If it is non-reacting system, just a simple mass balance equation, whatever you are giving, which will be coming out. And if you have accumulation, if you are operating in an unsteady state operation. Okay. So this is a simple mass balance equation. I am trying to use it. So here is my batch reactor. So batch reactor is the most widely used in the many industries also, as well as in the bioprocess industries also, because operating wise it is easier, And I mean, that is the one convenient we have in the batch systems. The contamination wise, everything we have a check. But with the batch react system, you cannot able to handle the large supply of your material. That is the one challenge in the batch reactor. When you are talking about production in a large quantity, the batch reactor does not work. You need to go for a continuous system. Okay. So I'm trying to apply the same mass balance equation here, where Fa naught is the initial the moles which is getting into the system, and Fa is the moles which is getting out from the system. And this is the rate of reaction which will be happening in the batch system, and dNi by dt is the accumulation term. And in the batch reactor system, once you start your reaction, you don't add any material into it, right? So your input and output typically will be zero. So that's why I put at zero. So your rate of reaction will be equal to your rate of accumulation. So once then you will be getting, I mean, if you rearrange and integrate it, you will be getting this expression. The time, the fermentation time will be a function of your XA and your rate. Okay? You can see here. 1 by minus RA versus XA I have plotted here. Okay, the area under the curve will give me the time which required for the batch system. So batch systems, you don't, I mean, you don't typically talking about the volume. You will be fixing your volume and how long I need to operate the system to achieve the particular conversion. Let's say if I happy with the 0.5 conversion, I can able to operate the system very, reduced time. I can operate in a lesser time. If I want to achieve 99 percentage or higher percentages, I need to operate the system in a higher, longer period of time. So that is the one implication you can able to get it from this particular graph. Okay. Now plug flow. So when my professor used to explain this plug flow reactor to us, he used to try to tell some kind of jokes so that we can able to remember. So I will elaborate the definition, then I will go for the joke. Now, in the plug flow reactor, if you see, the ideal condition is every particle spend exactly same time in the reactor. So how do we ensure that one? If you get only the flat velocity profile, then only let's say this is one profile, delta injection I'm giving in, and every particle spend exactly same time means it does not have any axial mixing. So it does not have any axial mixing, but radially it will mix infinitely. And every particle will come exactly same time. Let's say this strip particle enters at 0th minute. If I put another strip next to that one, at 5th minute, and this strip will leave at 10 minutes. The next strip which I'm adding after 5th minute, which will be also leaving at 15th minute. So here in the strip, no particle will leave, or the mean value of the mean time spent by the every particle will be same. So how do we connect to the real time world? So if you go to the Tirupati temple or any temple where the crowd is very higher, so what they do is that they will be sending the people, and if you see, let's say I'm entering at 0th minute, I'll be spending some 10 minutes inside that queue. See the god and then leaving from the premises. Now another person comes at 1 minute. Let's say I'm 0, and he is coming compared to me 1 minute, and he will be leaving the system 11 minutes. So like that, a perfect line will be formed, and every person spend exactly same time in the particular queue. So this is one typical example. But how do you achieving this flat velocity profile in the tubular reactor is difficult, right? So why it is difficult? Because your pipe should be smooth so that no slip condition will be existing. Even then, achieving this high velocity, flat velocity profile, you need to operate at a high flow rate. Whenever you are operating at a high flow rate, your volume going to be increased. So it is like everybody have a dream to marry with Aishwarya, but we never had a chances, right? So only one person had a chance. Like that, it's all about ideal, which never exists in the real system. That is the one definition we can give in for the plug flow reactor. So ideal was, that's why we tell that one ideal reactor, which never exist. Which will never exist in the real time world. Now, for the same plug flow reactor, if I write a mass balance equation, I have an input, I have an output, and I'm considering the accumulation term will not be there, and only reaction term is there. So when this is the mass balance equation at steady state. There is no accumulation term. So once I do that one, I'll be getting the rate. I mean, I just explain. So when a particle ends at 0 time and it moves along with the reactor, my concentration, if it is forming the along the length, the concentration increases. If it is consumed along the length, the concentration is decreasing. But at every one point, let's say this is a strip I'm talking about. Here, the concentration of every particle remains same. That means exactly it spent same time in the reactor. There is no axial mixing, only radial mixing will be happening. So in such a system, you have a variation along the reactor. We'll be taking a differential approach. So we'll take a small volume where the changes will happen at very, minimal. So, and then we try to integrate for the entire length of the reactor. So for the smallest region, this is the mass balance equation. If you try to write for the entire region, then you will be integrating from 0 to xa. So this is the design expression for your plug flow reactor, right? So in the plug flow reactor, what we are doing in the, I just explained the graph. So I'm plotting one by the rate versus the conversion. I'm putting it here. So the area under the curve is going to give me V by Fa naught. What is V by Fa naught? The volume which you want to construct, and Fa naught is the flow rate by which you will be operating it. Okay. So I'll be explaining how to fix this parameter and find out your volume requirement for the particular reaction. Okay. Now, for the same concept we apply for the mixed flow reactor, but mixed flow reactor, what is the ideal, what is the phenomena here? Whatever you add into the reactor system, since you have a stirring, at any particular time, you can see your substrate will be uniform or your product will be uniform. That's why in the continuous stirred reactors, you will be measuring your concentration at the inlet and you will be measuring in the outlet only. You never try to measure the concentration in the tank, because whatever the concentration in the tank, that will be the same in the output. So that is the one condition. It's a perfect mixing condition is the one ideal condition we can expect from the plug flow reactor. Since there is a very, you have a complete or uniform mixing in the reactor, and the substrate and the product concentration remain same at any stage of any portion of this reactor. So you don't need any integral differential approach. You can simply write the mass balance equation, and if you rearrange, you will be getting the same expression as that of your plug flow, but you can see that without integration it will be appear. So that is the only difference we have for the mixed flow reactor. Okay. Now at this point, we have, in order to arrive this design performance equation, how do we arrive? I have explained from the previous slides. Now you have some kind of clarity like how it has come. Okay. Now hereafter, what we have to see is that I am taking one example, that is plug flow reactor. So for the mixed flow reactor, one example I have taken it. So the design equation is V by Fa naught equal to Xa by minus Ra. So here, so you found it. What is the purpose of finding your rate expression? Because the rate expression will trying to help me the design of any particular reactor, conceptual design. Okay. Now this is the 4 parameter. Now in most of the education institute, what we do is that we try to give your Xa, and we also try to give the Ra, and we try to give your Fa naught, and you will be asking to find the V. And it is simple for you, and it's a simple rearrangement, and you can be able to do that one. But if you go to the real industry, they may not give your V, they may not give your Fa naught, they may not give your conversion also. So how do you, this is like n minus 2 cases, n minus 3 cases. Most of the exam, what we do, we try to give all options except that answer. Let's say in these cases, out of 4 parameters, I'll be giving 3 parameters data, and I'll be asking 1. So which is called n minus 1 data. So the students will be finding it. But industry is not n minus 1 problem. It can be n minus 2. It can be n minus 3. Why? I'll be explaining in this slide. So I'm taking a mixed flow reactor as one example here. So the Fa naught you are seeing here, right? The feed flow rate. So how do how to fix a feed flow rate? That is important. So let's say I'm living in a place where the demand for a milk or any material is 1 lakh liter per day. So based on the complete market survey, that means how much is the demand for the particular city, or how much the demand for the entire country, or how much demand for the export, all those things I'm calculating, and then I'm trying to find this is my output volume I want. That means I want 1 liter milk, 1 lakh liter of milk need to be supplied daily in the city. That is what my demand, market demand. So based on the market demand, I am going to fix my FA0. That is the inlet flow rate of the particular milk I am going to fix it. So this FA0 will come from the market survey. Okay, so if you plan to start any industry, you will be doing a market survey. So what is the requirement of the product, how much I need to produce, all those things you'll be trying to find. So that gives me the FA0 value. Once you find your FA0 value, then what do you do? So you need to you need to construct a reactor, and for that you want a rate expression. So rate expression, how do you find? I'll be explaining that one. So you will be getting one general expression based on your experimental data. You will be substituting here. So you got FA0 and your RA will be ready, and another unknown is your XA. How to fix your conversion? That is, it is based on your economics of the system. I have one example. Let's say, one example in the sense, if I want to have a 100% conversion, it will never try to, will be there in this, universe itself. So if you want to have a 100% conversion, you need to construct a reactor to the moon, from Earth to moon. Such a big reactor you need to construct. Why? I'll see this curve. You just see the curve. It increase and it goes as a straight line. It never try to touch the XA, because XA varies from 0 to 1 only. So if it is 1, it never try to achieve the 1. And if you extend it infinitively, it may touch the 1. So such a big reactor you need to construct. The area under the curve is going to be give you the volume of the reactor which you need to construct. Okay. Now let's say this is my conversion A. I just 1 minute. So this is the conversion this is for the 0.5 conversion. For the 0.5 conversion, my volume will be this much. Okay, and this is my this is for the conversion of this is for the conversion of 0.6. So this is 0.5, this is 0.6. Okay, now 0.5, the volume, from the curve, what we are able to get is the V by FA0, because if FA0 is fixed, then you will be getting your volume. So from here, I am calculating the volume. And for the higher conversion, this is 0.5, and let's say this is 0.6. So for 0.6, the volume will be this much. Okay, the area under the curve. So from each data, I can able to find the volume. I can able to find the volume because FA0 is fixed. So I have to ask myself whether I am happy with 0.5 or 0.6, because 0.6 leads to 5 liter of the reactor. But if the 0.6 leads to 10,000 liter, so which one will be trying to go for? Because obviously the material costs or construction costs also involved in any particular process. So I'm just giving an example. It never happened, but choosing the conversion, I give an example like this. Okay, so 0.5 you required only 500 liter, whereas in the case of 0.6, if you want to go, you need to construct 1000 liters. So just for a 0.1 conversion, you cannot able to build such a big reactor. Instead, you can go for a 0.5. So like that, based on the conversion, you can plan what is the volume you can able to construct. So FA0 comes from the market survey, and RA we will be finding in our laboratory by doing a simple reaction, and XA you need to fix it based on the market volume of the product or the construction amount of your construction cost of your reactor. So this is how a conceptual design of any reactor will be concluded. Right now we'll see. Now, so what we have discussed in the previous cases, each term, how you find or how do you get an idea about all those things. Now hereafter what I am going to talk about is the finding of this minus RA. How do I find the minus RA value? Okay. Now, if you are talking about a homogeneous rate expression or a homogeneous system, and the rate expression typically will have one rate constant and another concentration term. This is the two term is there. But you have learned that any reaction is depends upon concentration of the limiting reactant as well as the temperature of the system, like that you have studied. But the rate directly proportional to the concentration of the particular material only. So where is your temperature effect on that system? Because many people does not, even I didn't tell my students that what condition I'm operating a reaction. Okay, if we see the exact answer, the rate expression is the function of temperature also and a function of concentration also. So the concentration is this term and the temperature dependency term is my K. So most of the time I'll consider the K as constant because I'm running a system as isothermal condition. What is isothermal condition? I'm operating at the same temperature. I'm not changing my temperature. If I change my temperature, the reaction will be affected by the temperature. How does it affect? You have Arrhenius effect, which tells that the reaction rate is the function of temperature. You can see here. Okay, so if you are operating your system as isothermal condition, you don't want to worry about the rate constant. Whereas if you are operating your system uncontrollably, that means you don't control your temperature, then K also influence your rate of the reaction. Okay. Now, if you enter into the reaction system, then you have two type of reaction. One is elementary reaction, another one is non-elementary reaction. So elementary reaction means this is my stoichiometric equation. That means reactant A and B reacts to give C. That's it. Okay. Now, if you see the stoichiometric equation and the rate expression, okay, I have mistake here. That means CB. I need to write it. Okay. So the stoichiometric equation and the rate expression both are same. Okay, the rate, or otherwise also I can tell the rate expression resembles the stoichiometric equation. Here also I need to write CA also. So here also I need to write CA also. The stoichiometric, sorry, this is CA and this is B. Okay, okay. So the rate expression exactly resembles the stoichiometric equation of my equation, stoichiometric equation. In such cases, we call that reaction as elementary reaction. So whatever we see, that will be as your rate expression. That means you don't form any intermediate, or the chances of chances of getting intermediate and then consumption is very fast in those reactions. So you don't give importance for the intermediates. Whereas in the non-elementary reaction, you can see this is the same reaction I have written A plus B equal to C, but the rate expression is something different. So this is not resemble to each other, right? So these are all not, following the stoichiometric equation, the rate expression. So in such cases, we call that reaction as a non-elementary reaction. Why this kind of complex rate expression has come because of the intermediate formed in the particular reaction. That means A plus B not directly giving my C. Instead, the A plus B reacts and it can form some intermediate. Those intermediate also play an important role that converts into C by slowest step, by slowest rate, or it can happen at a faster rate, whatever it may be. So in the case of biological system, we use the Michael-Menten equation. That means the substrate plus enzyme reacts to give a product. Okay, so substrate plus enzyme reacts to the product. So if this is the simplest, if it is following a elementary reaction, what is the rate expression I will be getting? That means minus RA into, minus RA equal to K into the concentration of the substrate and the concentration of the enzyme. That's what I will write it. But the rate expression is different. You can see here. So when you have a complex rate expression, then it means that these the reaction is not elementary reaction. It has a multiple steps as an intermediate. Those also influence the final rate. That is the meaning of that one. And the rate can be related like if you because whenever people write rate expression, they will K only. A common one. So if you write a rate of A, the rate constant is Ka. If you write the rate of B, the rate constant is Kb, right? So when you relate this the rate by which A is consumed, or the rate by which B is consumed, or the rate by which E is formed, those things can be related by this equation. So what I have written is, let's say this A is my stoichiometric coefficient. Usually I write A, small a. So here also I have to write small a. Okay. So the stoichiometric coefficient before the reactant, whatever I have the coefficient, I need to divide that one with my rate. Then I can able to relate the rate by which A is consumed, which is equal to the rate by which the B is equalized. So this will be helpful when I want to find the conversion of C. I can able to, I mean, if I am able to read only the A, then I can find the rate of A, which is also equal to C, by this kind of relationship. Okay, that's the purpose of relating each rate. Now, various homogeneous reaction I have listed. It can be a first order, second order, reversible, irreversible, parallel, series, like that. So many cases discussed in the 11th scale book. And the corresponding rate expression can be, or it can be more than that also. So for this single reaction, there can be this much possibilities there. This much possible rate expression can be there. So how to find whether it's a zero order, first order, second order, or I mean non-linear or anything. So how do we find that one? So for that we have set of techniques. One is the differential approach, another one is integral approach, and third one is the initial rate analysis and half-line method. So differential, integral, and half-life method are given in the 11th scale book itself. Regression is just to also can be used to find out the rate expression for the experimental data. And you can use multiple packages, Excel, Polymath, MATLAB, to analyze the data. I have used Excel. I'll show you like how I found it. Okay. Now, in the cases, I am just talking about the integral method. It is the easiest method. One can able to find it. Okay. Now, integral method, in any rate expression, this is the rate expression. What are the unknowns here? The K is the unknown here. The rate constant I need to evaluate, as well as the order of the reaction I need to evaluate. These two things are unknown for any rate expression. So in the cases, first in the integral method, I used to assume the order as my fixed quantity. I mean, I can assume the order of the reaction. Let's say I'm assuming the order of the reaction as 1. So that's what happened with the first expression. That means minus Ra equal to K into Ca. And K I don't know, but order I assume, since the order I assumed 1, I have put the power of 1. Okay. Now this is the rate expression. So just linearize this expression, you will be getting this expression. That means minus ln of Ca divided by Ca naught equal to K into T. So how does it looks like? It looks like y equal to mx. Simple regression equation or simple straight line equation. So this is my experimental data. So what I did, I did a reaction. I started measuring the concentration of my reactant with respect to time. So those data also I have shown over here. At 0 time, whatever the concentration I have, that is my Ca naught. Okay. Now try to substitute the Ca naught and Ca value with the corresponding time here in the expression. So I'll be getting a set of data. Let's say if I put first 0 reading, it will be 0. So second reading, if I'll be getting a 1 data. So those data I'm plotting in the graph. The dotted lines are the experimental data. So once I put my experimental data here, since this is the straight line equation, I have used it for my experiment data. So my experimental data has to follow the straight line equation, right? If whether it follows a straight line equation, so what I drawn is the regression line, and which passes common to all the points, but it shows that these data points are not following a straight line, right? So if it is not a straight line equation, so what I need to do is that I need to change the order of the reaction. So I can consider 0 order reaction. So if I consider 0 order reaction, dc by minus dca by dt equal to k, and then I will be linearize that expression. And once I linearize the expression, again it comes in the straight line equation. Try to substitute the data into the linearized expression, then plot it. See that the data follows a straight line equation. So like that, you can change the order, you can incorporate another molecule also here. That means it is also a function of another component also. Like that, you can increase the number of reactant also. So like that, if you try to do that one, I mean, it's a trial and error based methods only. You'll be keep on doing that one until you will be satisfied with the data, that the data points after substituting into the linear expression, it has to follow the straight line. If it's not following the straight line, then you have a freedom to change this one. So there are infinity attempts you can make it. So in order to avoid these things, people try to use the half-life method. We use that one. So in the half-life method, the order cannot be a order cannot be a integral. It can be a point. I mean, all the time it may not be a like a complete numerical. Let's say 1 or 2 or something like that. Sometimes it can be 1.2, 1.3, something like that. Those things you can able to get it only if you go through the half-life method. And you have another method called a differential method. What we do is the rate will be plotted against the concentration. So there you will be writing a tangent lines. Then you will be trying to find the slope of that one. That also trying to give you the constant value, that is your k as well as your rate constant. Those you will be getting this equation. So why I'm trying to find the kinetic expression? Because this kinetic expression I can able to directly substitute in the design equation, and whatever the time or the conversion, if I substitute there, it will try to give me what is the rate by which it form or it will be consumed. So that is the purpose of finding the model, giving a model for this kinetic expression also. So for the biological people, we uses mostly the enzyme reaction. And if you use enzyme reaction, it is very common to use the Michaelis-Menten equation. This is the kind of Michaelis-Menten equation, and it is a non-elementary. You can see this is the stoichiometric equation. This is the rate expression. Both are not resemble each other. So it is a non-elementary. That means you have an intermediate which is also played in the overall rate of the reaction. Okay. And yes, what I am trying to give is the substrate which limit the particular reaction. As you know that you have n number of substrate, but certain substrate will be limiting the reaction. That means the availability determines the overall rate of the reaction. Okay. If you are using a cell for the biological system, then you can use this expression. This is we call as a Monod equation, where also the substrate which limiting the growth of the organism will be considered in the system. In chemical reaction engineering, if you see the 11th sphere, most of the time they have given the integral or differential approaches for the molecularity up to 3 only. Molecularity means how many reactant involved in the reaction. Though you may have a 10 reactant, but out of 10, only 2 or 3 is going to be determine the rate of the reaction, molecularity. Okay. So the molecularity in the chemical reaction is maximum 3, but in the case of biological system, we exceed that one. That's why we go for a screening of method and then trying to find optimum value of the point. So if you see all those experimental data, you can understand there are n number of molecules. Molecularity will be there in the kind of in the case of biological experiments. Okay. Now other models. So people started using the Monod equation to model the particular system, just to have a kinetic expression that they'll be substituting in the data where we want to design a conceptual design. So they try to substitute, but sometimes it does not work, because not only chemical system, biological systems are more sensitive to the inhibition caused by the substrate or inhibition caused by the product. That means for an example, the human can able to eat the food at one limit only. He cannot exceed that one. So something like that, the organism also have a limitation in eating the food, or whatever the product it secretes. Sometimes it kill its own cell system. So such a system we have, complex systems. So for that, the rate expression has to be changed. Like that, I have n number of rate expression changed for the such a system. If you feel substrate inhibition, then you can use this expression. So like that, different people, testers, modified Monod equation has developed, and those things have changed. If you see more than 2 substrate limiting the reaction, then the same Monod equation can be written like this also. Okay? So such an expression you need to write it. Then what is the unknown here to find? The mu max value, K1 value, K2 value is the unknown in the rate expression. Once you find this one using the experiment data, your kinetic expression is ready. you can go for your design of the reactor. Okay. Now, after seeing all the things, now we can able to realize what is the purpose of finding the rate expression for any particular system, just to want to design any reactor. Okay. Now, what are the informations are required to design a reactor also we have explained. Now, I'm just entering into the heterogeneous reaction system. So, as I said, if we have a same phase or they are miscible, the mixing is not a big deal. You don't require any stirring or anything to mix each other. Okay, so the reaction is only depends upon the reaction speed of the substrates only. It does not depends upon any other physical influences. Whereas in the case of heterogeneous system, the reaction is also depends upon the mass transfer of the system. So I'll be trying to explain a biological system. Let's say in the fermenter, you'll be bubbling air into the system, and you'll be the cell will be utilizing the oxygen from the air. Okay. Now I'm starting from here. Okay. Now this is my this is my air, and if you have a air and you have a liquid system, then there will be interface between the air and the liquid. So that is the one barrier for which my oxygen facing a problem to travel through that one. Okay. So once it travels, then it enters into the bulk liquid, and you have a convective flow or convective. There will be a mass concentration gradient. Then there will be a movement, and if it's a mixing is there, then convective flow is there. So your concentration in the bulk liquid of oxygen will be uniform. Once it come into the cell is a solid material, and the solid is surrounded by a liquid film that will be offering a resistance. So the oxygen has to diffuse through the liquid film, because the liquid film is stagnant around the solid. So the concentration gradient in the film is very, very low. So the transfer will be very, very limited, because every transfer process is limited by the concentration gradient. Then once it reaches the cell also, the cell has to uptake that one, and the cell has the liquid system inside cytoplasm, and then it takes to the place where it is required. So such a mass transfer effect will be there. So even then, the biological system, people says that it is homogeneous. So they will be neglecting this resistance offered by the flames, resistance offered by the stagnant flames. All those things they reduce. They say that once I bubble the air and it simply goes into the system, because I'm considering a cell as a colloidal. Colloidal means it does not have any shape. So I just like a liquid, it will be there, and the gas will be traveling to the liquid. So that is the assumption we try to make it when we are going for a homogeneous system. If you see the oxygen transfer is limiting the overall reaction, then mass transfer effect has to be incorporated in the rate expression. And there will be a definition called overall and absorbed rate or global rate. We say that. That means you have more than one phases. That means movement of one phase to another phase in the reaction system. Then the mass transfer term has to be considered in such a systems in the chemical kinetic terminology. Okay, such a systems you will be observing one rate. It is a combination of mass and chemical, both. It has a physical and chemical factor. That rate we call as a global rate of the reaction. Sometimes it can also called as a overall reaction rate or absorbed rate reaction also, which is not the exact chemical engineering rate by which it is getting reacted, because mass transfer is there. So whatever we are seeing is the absorbed rate or global rate, which we need to consider. Okay. Now, in a simple example, non-catalytic reaction, when you supply air, let's say oxygen, you are supplying a pure oxygen. So when it contact with the carbon, that means coal, at high temperature, it burns and gives me the CO2. It's the simplest one. But if you see the carbon, the solid material, the coal is surrounded by air or the oxygen, which will be a stagnant flame. So from the air or from the bulk oxygen, the oxygen has to diffuse through the layer, and then it has to go to the surface of the solid and then getting reacted. Even after getting reacted, the carbon dioxide which is formed in the reaction will has to diffuse through the flame, and then it has to come out from the bulk air. So this is the portion where it determines, this is the flame, the stagnant flame, which will also determine or limits the rate of the reaction. So whatever it limits the rate of the reaction, you will be incorporating those things in the rate expression. You can see here the mass transfer effect as well as the chemical effect. The chemical kinetics, both the things are given here. Finally, I will have some common or global rate in which the gas transfer as well as the kinetic effect, both the things are added to each other. Okay. So this is how the mass transfer and the reaction term can be incorporated. Sometimes the mass transfer is the slowest step than the reaction rate. Then your reaction rate can be a mass transfer. That means the minus Ra equal to this term alone you can represent. Your reaction is depends upon the rate of transfer in the interfacial film. Sometimes if your interfacial film is very low because of the perfect mixing, and you don't have any typical interfacial area, then the rate of the reaction is much slower. Then compared to the mass transfer effect, your reaction rate is slowest one. Then the global rate, which is depends upon your reaction rate only. There you can skip your mass transfer rate. Okay. So depending on the situation, you can consider your reaction rate or the mass transfer rate to be incorporated in your observed rate. Okay. So now at this point in the heterogeneous system, the rate of the reaction is the function of concentration, temperature, as well as the transportation coefficient. That means mass transfer also come into the picture. That is the real meaning of that one in the case of heterogeneous systems. And some simple design problem. Let's assume one plug flow reactor. I am having it. I am performing an enzymatic reaction. I have given the initial concentration. The XA also have defined, and FA naught also. FA naught also have given what is the rate I need to operate in. So enzyme reaction means you have a Michaelis-Menten equation. This is the rate expression. I found it in the laboratory scale. So what I have found is the constant value as well as Vmax value. I can able to find it in the reaction. So I know the rate expression. So what I need to find, how much volume I need to construct for such a reaction, I need to find it. For that, I need to recall the design expression for the plug flow reactor. What is the design expression for the plug flow reactor? V by Fa naught equal to 0 to Xa, dxa divided by minus Ra. Okay. So I need to substitute the Ra value. So whatever I reported previously, this is what I found in the experiment data, using the experiment data. This one will be substituted here. Once I substitute, I am having this expression. Okay. So the K1, K2, and the volumetric flow rate, what I am operating, the initial concentration, final concentration, how do I find? Because I said my rate of conversion is 90 percentage. 95 percentage, I think. Okay, 95 percentage. So now 0.05 into initial concentration is my final concentration. So that I am substituting the equation. I have found the volume, that is 1 meter cube in the case of plug flow reactor. If I want to operate the reaction in the plug flow reactor, what I have to construct is 1 meter cube. Remember this one. If the same parameter I am operating in a mixed flow reactor, that means CSTR. If I am operating in the CSTR, so what is the volume requirement? So I need to find it. So what is the rate expression for the CSTR? This is the rate expression. So XA I have it, CA naught I have, minus RA also given, and I need to find the volume of the reactor only. So in the case of volume, I have found it. The volume, I'm just substitute data, I am getting the volume as 5 meter cube. You see, the same system, same concentration, same conversion for the plug flow reactor as well as PFR reactor. The CSTR given higher volume. That means I need to construct a bigger reactor for the CSTR, whereas for the plug flow reactor, it is 1 meter cube only. So compared to like 5 times, it is increased for the same system, for the same conversion, for the same conditions, whatever I employ. So now you can able to understand. If I construct a plug flow reactor, I will be getting a higher yield, or I can construct in a smaller volume itself to achieve the particular conversion. But that is for the ideal condition. Whatever the plug flow reactor I have given, that is for the ideal condition. That means isoretic. It never exists in the real time. That means maintaining a flat velocity profile, you need to have a high flow rate. If you have a high flow rate, you cannot have a bigger pipe. You need to have a smaller pipe only. So if you have a smaller pipe, you need to construct that much volume. You need to have a straight pipeline which connects from Kanyakumari to Delhi. Such a straight line pipe you need to construct. Then you can maintain a flat velocity profile. Because if bend is there, then pressure loss will be there. there will be a question about the flat velocity profile. You don't get it. Many algal growth people try to use fluctual reactor. They make bend and then they use the flux flow reactor. They have deviated from the flux flow reactor. So constructing an ideal flux flow reactor, it is not at all possible. That's why most of the time we go for the CSTR reactor in order to achieve the particular conditions. Remember, if you are operating a continuous reactor, initial setup is difficult. But if you want to have mass flow rate or higher productivity, continuous system is the best one. Even in the bioprocess engineering system, people are trying to move from batch system to the continuous system. Okay? That has advantages. I mean, economic wise, it also saves money. Okay. So my professor Krishna used to tell that the dream flowchart is the reactant comes in and it will react in the reactor and you will be getting a product. So though no physical process for the processing of a product or something like that, means the product enters, I mean substrate enters, 100% it convert into product. So no need of any physical process after the reactor. If at all there is a decrease in the conversion, then you need to separate reactor and product. Then you need to have a distillation column or anything you will be adopting as a physical process. If your reactor gives me 100% yield, then all those unit operations before and after, of your reactor system will vanish. This is ideal case and dream case also. Okay. And I finally acknowledges Professor Krishna as well as my boss Professor T. Panda, who have given insight about the chemical reaction engineering. And most of the slides, whatever I have shown, I have taken it from Krishna's slide, who came for me for the reactor 1 FTP program. He came and he has taught to all the people in a better manner. And if you want to understand more about the chemical reaction engineering, homogeneous and heterogeneous systems, you can follow his NPTEL videos. He has recorded all those class lectures and he has given in the video. And NPTEL is one of the promising place where, let's say, I have not qualified JEE exam. I have not got admitted in any IIT and NIT, and I never had a chance to listen those lectures by the IIT professors. But I mean, in the previous times. Nowadays, it's not the case. You can learn. You can start your career at any college, any places on your village, near to a village, or any place you can stay, and you can listen your IIT professor lecture simply from the NPTEL videos. It is open, and you can learn whatever you want to learn from that one. So technology brought every people closely connected to each other. So that is one advantage we have with the NPTEL videos also. Okay. And thank you for listening my words for this lengthy period. I have troubled you a lot. And if you have any questions or anything, please post me. I'm ready to answer.
Okay, sir. Thank you for your lecture, sir. So we have a few questions from our participants, sir.
Yes, sir.
The first question is, what is space velocity in the reactor?
Space velocity. It is
Yes.
one inverse. Typically, if I want to define, it is one inverse of your space time. Space time is like V by F A naught. People used to define. That means volume by volumetric flow rate. So, how much time a particle has to spend in the reactor to get the particular conversion is defined as residence time. Actually, how much it is spending, and if you allow the molecule to spend more, your reaction is more. Your conversion is going to be higher. If you spend less time, your conversion is low. So that is what happened. That is this space time, and phase velocity is one inverse of that one. That means volumetric flow rate divided by volume. The time, how much time it spends in the reactor.
Okay, sir. The next question is, for the same volume, which reactor has the highest conversion, whether it's a CSTR or PFR? Will it change for positive or negative order reactions?
Yes, correct. Your question is correct. So once you are getting your kinetic expression, you can substitute in the design expression, what I have shown over there, and it will tell you what is the volume of the reactor you need to construct. And PFR, nobody will try to construct the PFR because maintaining a flat velocity profile is ideal. It never happened. So whenever you have a curved, or you can see the laminar flow pattern or something like that, particles spend a different time, and your conversion, whatever you expect, it may not happen. And such a big reactor constructing in a smaller volume, it will be difficult. That's why many times people go for a continuous state reactor. And one thumb mark is that I think 1,000 ton, less than 1,000 ton, you can go for a batch. If you go for more than 1,000 tons, you can go for a continuous reactor. Continuous reactors are better always, because if you talk about economics, continuous reactor survives. Batch reactor does not survive.
Okay, sir. The next question is, to design a new reactor, what are all the steps to be followed? How to get the experimental data for designing?
So whatever I have talked about, it is a conceptual design. In conceptual design means it will give you one value of reactor, let's say 5 meter cube or something like that. It does not talk beyond that one. But again, you learn the chemical reactor design, right? So in the case of, I'll explain briefly. In the case of biological reaction system, though I get a volume, I need to fix the height to the diameter ratio, H to D ratio, like that people used to say. This has to be fixed, because this is very crucial in terms of mass transfer of oxygen in the system. That means if you have a very height and diameter is length, that behave different. And if you have a very big diameter and a small reactor, that react different. That means the residence time of your air bubbles has to be appropriate, so that the mass transfer will be happening in a perfect sense. So in such a cases, the H by D ratio has to be fixed. Once you fix your H by D ratio, then nothing more than that. Simple mechanical design. Those things can be done. First conceptual design, then go for a mechanical design.
Okay, sir. The next question is, which reactor arrangement will give the maximum conversion? PFR followed by CSTR, or CSTR followed by PFR, and why?
Yes, actually, I have not touched all those parts. It is all about the contacting pattern. Okay, so in the 11th PL, they have talked about this one very clearly. I mean, which one has to be followed, which one has, which has to be connected in series, which one has to be connected in parallel, which gives you better results. But mostly, plug flow reactor gives the more yield than your CSTR reactor. So plug flow followed by CSTR may be the appropriate, and again, it depends upon the kinetic contacting pattern of the reactor. So there is no general rule for that one.
Okay, sir. The next question is, what's the relationship between reaction engineering with fluid mechanics and thermodynamics?
If you connect all those things, let's say I'm talking about plug flow reactor, I said flat velocity profile. It is all about the transfer phenomena. That means all particle has to spend exactly same time. That is the ideal condition. So it is again hydrodynamic condition. I'm talking about fluid mechanics only. And I have said, whenever you change your temperature, the reaction rate will be changing. As I introduced Arrhenius equation, those all comes from thermodynamic concepts only. So maintaining a isothermal condition, the heat, if it is exothermic reaction, how much heat need to be removed from the reactor, those requires your thermodynamic heat transfer knowledges.
Okay, sir. The next question is, explain why the number of CSTR connected in series is equal to 1 PFR.
Yes, correct. Good. Actually, CSTR is the complete mixing condition, right? So if you connect a CSTR in series, it is just like you consider a plug flow reactor and then cut that one into small strips, and each small strips are considered as mixed flow reactor. Why I am saying, in the plug flow reactor, in the small strip or the smaller area I have shown, in the area, every particle spent exactly same time. So the concentration of the product or the reactant in the strip is uniform. It is resembles as that of your CSTR assumption. CSTR, what is the assumption? In the reactor, every loop and corner, the concentration of substrate as well as product is uniform. So that is what happening in the plug flow reactor also. Don't see the entire length. Take a smaller strip, and in the strip you see every particle spend exactly same time. So the conversion of the particular particle will be same. That means the concentration of the reactant as well as substrate on the strip is same. That's why we call multiple reactors, multiple CSTR connected each other, which resembles as plug flow reactor.
Okay, sir. The next question is, in case of large volume process, they are using continuous reactor, but there is a conversion problem. So how they choose a reactor, whether it's a CSTR or PFR?
I think choosing or the parallel or series I have explained because I'm not clear. I'm not clear about myself itself. Okay, so in the case of fixing a continuous reactor, initially you need to work a lot on establishing the continuous system because once it's on, it will never stop in between. You need to operate it continuously. But establishing a continuous reactor is must in the case of cost effective also. Let's say if you are operating a batch system, so the batch system can run for the reaction which is very slower. You will be going for the batch systems. Let's say microbial reaction. You will be doing this reaction for 10 days and cleaning. After that harvesting. So it takes another 10 days. So almost one batches it takes 20 days. Whereas in the continuous system, you are continuously pumping and your organism is kept ready. So once the reactant comes, the organism started eating that one, you will be getting a product and you need to operate the system lesser than the dilution rate so that your cell will be there in the system and you do the job and you will be getting a continuous product out. Even it is a laser conversion also, you will be getting continuously and the unreacted one, you can send it back also. By that one, you are not wasting your substrate, you will be getting your product continuously. But the one typical challenge is that in the biological system, though chemical is very simple, like you get a continuous system, you can separation will be easy if it is solid or liquid, or if it is immiscibly liquid, you can keep it for some time so that it will be separated. But biological system is not like that. You need to do lot of downstream processing for that one. But even then, biological system they are moving towards the continuous system. That means continuous chromatographic system they are developing to achieve the continuous production as well as continuous separation. That people are working on it.
Okay, sir. It's a last question from the participant named as Jerry Peniel. Which reactor is commonly used in petroleum industries?
I don't have much idea, but once I went to the CPCL and some other industry, it is depends upon the purpose they are using. Sometimes people use a packed bed reactor. I mean, if I want to separate the sulfur from that one, they do that one. Otherwise, some in the CTEC petrochemical industry in Chennai, they use a glass column reactor. Column reactor. Okay, so in the column reactor, they pump reactor and substrate. I mean, I think parallel or I mean anti-parallel, and they react, and then they will be getting their product out. Most of the time, CSTR they use to employ. The plug flow reactor is not quite common in many of the industry, except that algae industry. Those uses the continuous plug flow reactors with some kind of adjustments.
Okay, sir. Thank you for answering all questions, sir. And thank you for your valuable time, sir. I want to conclude this session with a vote of thanks. I would like to express our sincere thanks to our guest, Dr. A. Srinivasan, for sharing his valuable ideas about biological reaction engineering. I would also like to thank our beloved HODs for their moral support and guidance. I am very happy to express my vote of thanks to our staff members and participants who have made this webinar a great success. Thank you. Thank you all.
Thank you, sir. Thank you all for listening this much video.
Thank you, sir.